Now I'm going to introduce our two speakers, and then we go. So Anna will be our first speaker. She's the team leader of the machine learning team in the innovation section of ECNWF. She helps coordinate the broader machine learning activities and also coordinates the Anemoi development with a focus on the core packages. And then after Anna, we'll be hearing from Harrison, who is a research software engineer in the development section of ECNWF. He contributes broadly to the Anemoi ecosystem overall with a focus on the inference side of the pipeline. He also contributes to EarthKit and Forecast in a Box. And with that, I hand over to you, Anna.
Great, thanks a lot, Julia, and good afternoon, everyone. So today, for the first part of the meeting, I will be talking to you a bit about the Anemoi training package. So now I hope that for some of you, this slide is familiar and you are almost all an expert of this, because we already saw this one in the first seminar on Tuesday, where we learned about datasets. Then yesterday, Mario talked to you about Anemoi graphs and Anemoi models. And then today we'll be sort of like closing the circle and we'll be learning about Anemoi training. That's the first part of the seminar that I'll be doing. And then Harrison will be talking to you about Anemoi Inference, that if we wanted to understand what are those two packages about, you can see those as the sort of like pipeline packages that allows you to first train the model with the data set, the graph, and the model that you define, and then run inference to generate new forecasts. So a bit about how Anemoi training is designed. So Anemoi training, as we said at the beginning, and similar to the other packages, it's a Python-based package, which is open source, and in particular, training is built on top of PyTorch Lightning and Hydra. And basically, it supports larger scale training, including both multi-GPU and multi-node training. And it's basically a highly configurable package that allows you to define your training setups by using YML configs. It does have support for more sort of advanced tools like profiling, in case you want to know the footprint of your model from a runtime and memory perspective. And then because training a model is key to also keep track of your metadata and the results of the metrics, it provides support to common experiment tracking tools like MLflow. So I will be relatively quick about this because Mario already gave you a bit of an overview. But yesterday you saw that there is a sort of range of different models that you can train in Anemoi. Those includes forecasting models that are both deterministic and probabilistic. So in terms of probabilistic models, it's worth saying that there are two different flavors. So you have what we call sort of like ensembles trained on a probabilistic score that we commonly refer to as CRPS-based model. And then we also support diffusion-based generative models. And then both for the probabilistic and the sort of like deterministic model, there is a second sort of degree of freedom, which is the spatial coverage, because it's important for us as a community that the models that we trained are both for global coverage, but also regional coverage with limited area model and stretch grid models. It's also important to say that there is other sort of flavors of the model. So this is a recent feature that we added last year, which is to be able to develop autoencoders, which basically these are models that sort of are in under active research, but look to enable scalable latent space modeling. And basically they are the sort of like key cornerstone to be able to do downscaling and other type of reconstruction tasks. And the idea with these autoencoders is that they would allow you to, because they just have a sort of like an encoder and a decoder, they look to learn a compressed spatial representation. So the idea with these autoencoders is that you can first train them and then combine them for other type of downstream tasks. The other two developments that I wanted to briefly mention before we start to look at the configs is basically it's a major development from last year, and is that Anemoi allows you to train with different data sets. So you don't have to just have one encoder for ERA 5, rather you could have multiple encoders with different reanalysis data sets like Sierra and ERA 5. Or at the same time, you could also have different decoders for either you could have one for atmospheric variables and then one with higher resolution for just the surface variables. In the time dimension, it's also possible to sort of like the model can just, we talk on Monday how these are autoregressive models for forecasting, and it is possible to forecast just one time step, but it is also possible with certain settings to allow what we call multiple output, so that rather than, let's say, forecasting t plus 6, we forecast at the same time t plus 6, t plus 12, and t plus 18. And then, as we said, there is also sort of like the downscaling approaches. At the moment, we have higher temporal resolution downscaling supported as part of the framework, as you can see on the left, where and then it is under active development, the support of spatial downscaling, which, yeah, as I said, it will be supported sometime this year. So now let's try to look a bit more at Anemoi training, and let's learn how you basically configure your own training runs. So to do that, it's important to understand that Anemoi training kind of like it's all around it's basically about setting up a Python lining trainer. That's sort of like the core object. And then this object has like different interfaces. So basically, this object will generate a checkpoint object that will be the interface that connect Anemoi training with Anemoi inference. There is also the sort of like model architecture that the trainer takes as an input. This comes defined by Anemoi models. The trainer also takes as an input the sort of graph creator, which is the object that we generate with Anemoi graphs. And then it also takes a data set. And for that, we basically call the sort of open dataset API from Anemoi datasets. So that's a bit of the overview of the different interfaces between Anemoi training and the different packages. In terms of like, how do we run an Anemoi training? Well, the first thing that you need to do is to define your own config, YML config. And as I said, this is based in Hydra. Because it's basically highly configurable and allow you to have nested configs, which are then, because of the number of different parameters and options, it comes very handy to control all these different sections. And here in the slides, you can see essentially an example of the different sections that you can have. And basically, Hydra allows you to encapsulate each of these different sections, and then you can just kind of go into the different subfolders to better encapsulate the different areas. In terms of the config groups that we have, in the next slide, we can see them a bit better. So we have for now a total of 8 config groups. We have data and data loaders. Those are the ones where basically we define what variables what data set we want to train with, which variables of that data set we want to use, and then in the data loader we say what is going to be the split between our training and validation data set, and basically the sort of like batch size and all the parameters related to data loading. The diagnostics section is related to callbacks for basically being able to generate plots if you want to evaluate your model as you train, specify and configure how you want to save your checkpoints, and other things related to callbacks. System is essentially the folder where basically you would need to say where do you want to save your data. So where you will be saving your checkpoints, where you will be saving your output logs, and also where is the input data. So where is the path where you have your data set stored. And also here you have what we call strategy, which is to define your hardware resources. So how many nodes, how many GPUs, and if you want to enable model parallelization, this is where you would do it. The graph recipe goes under the graph section, and similarly the model recipe or architecture goes into the model folder. And then the last two are the task and the training. So the task, you could think about it as basically It's a type of object that defines the I/O structure around training. So basically it tells you how many time steps you will need to load as model inputs and which ones would be used as outputs. So it's a bit of like, okay, do I want to load t-6 and t+6, t-6 and t0 to predict t+6? This is a bit where you then configure the task. And then the training is the rest of the sort of like training mechanism. So basically you will then define which your upper parameters, such as the learning rate, the loss function, and a few other things related to the training. In terms of how then you go, once you have your training config to submit a training experiment, is basically through the CLI. So there you would need to run the commands that you see in the slides. So to start generating a run, the first thing that you need, if you want to run Anemoi training, you would need to run Anemoi training train and then specify the config name. There is the CLI also includes a config generation command, which is the first one that you see here, config generate. But it's worth saying, if you try to pip install the repo and run this command and then go into Anemoi training train, the expected behavior is for the code to crash, because the configs templates that we've included in the repo, those includes a lot of question marks. Those question marks are actually fields that you are expected as a user, as a developer, to fill. And those include things like what data set you want to use, where do you want to save your logs. So these are fields that you need to make sure you configure correctly before the code can effectively submit a training run. So yeah, there is a few things about how to edit your configs that we can see in this slide. So as I mentioned before, we have support for Hydra, which means that basically you can do there are different flavors and you can pick your favorite one to go and edit your configs. You can do that from a top level config. So that's a bit like the option 2, where basically you have a template and then on that same template, you override the top level section. So in this example, you see there, we are overwriting the system group and overwriting the parameters for the name of our graph, the data set, and a few other things. You can also go into the sort of like config, nested config in the subfolder and edit that directly rather than in the top level. And the third option for you is to override the fields directly from the CLI. So that's what you see, where basically we are including, apart from the config name flag that we had in the previous example, a way to override the field for the system input dataset and tell Anemoi training that we want to use my dataset name SAR in this case. So yeah, the first thing that I would like to say, if you're looking to use Anemoi training, is for you to familiarize with this config system, and then to also think about what data you want to use and how to fill these sort of question mark fields so that then you can run the code effectively. Yeah, so this is a bit what I was just saying as a summary, that you have up to 3 options for how to configure your config. This is very handy because, for example, if you have in your models group 3 different architectures, so a GNN, a graph transformer, and a transformer, which is the 3 main type of architectures that we support, you could just swap the architectures from the CLI directly, passing this model equal and then the name of your config. So yeah, the configuration is very flexible and allows you to swap these things quite nicely. The model configs, I would also suggest that the best way for you is to explore the repo, because they are quite, the configs are getting quite big, so making them fit in a slide is not always easy. But just to give you a bit of an overview, you can find them within config/model, and there you can find within the repo a set of templates for different architectures that we are using. And then if you click in any of these YAMLs, you will see a list of parameters. So for the model, common things that you need to configure is the number of channels, so essentially how big you want your model to be. And then you usually have a section to define the encoder, the processor, and the decoder. But there is also other things, like, for example, if you want to activate the skip connections, or if you want to apply any type of sort of like physical constraints through boundings. In terms of data loading, I also wanted to briefly mention to you that in Anemoi, variables from a training point of view, let's say, they are sort of classified into prognostic, forcing, and diagnostic fields. Basically the main difference between them is that forcings are input-only variables. So those are variables like, let's say, land sea mask or solar insolation that can be either static or dynamic, but that we want to pass to the model, but just as an input. So those are not considered as part of the sort of model optimization. Prognostic, on the other hand, are those variables that the model will take both as an input as an output. So examples of variables that we in general configure as prognostic variables can be either temperature, humidity, winds, and then diagnostics are output only. So an example is that precipitation is usually a diagnostic only variable, and then what that means is that this is a variable that the model don't see as an input, but rather generate as an output. So yeah, this is an example of the sort of like data loading config, and as you can see here on the right, you have to define out of the data set that you will be using which ones will be your forcings and which ones will be your diagnostic variables, and the rest of the variables that your data set contains that are neither forcing nor diagnostic, and those are considered as prognostic. And yeah, I think it's also worth saying that you, in the sort of like data loader config, you can also you have flexibility to also define if you want to drop variables from your data set that your data set may include, but you don't want to use as part of the training. So there is also a possibility to specify those. There is also the next sort of like section, if we kind of like keep going through this list of 8 group sections that I mentioned, is the sort of training settings and tasks. So the tasks, you can find them under config tasks, and in this slide you're seeing an example of the sort of forecasting task, and there you can see things like, for example, the rollout. So rollout is basically how you want to train your model in an autoregressive way, where basically this is traditionally used to allow the model to learn patterns over longer times. And then, yeah, here you also can define how many inputs the model may take and a few other fields. Similarly, in the training section of the configs, you have a few examples on these slides. And a key aspect that you need to define within this group is your loss function. So Anemoi supports different type of losses, both including deterministic and probabilistic losses. And here you can see a list of all the losses that we have, but I would also suggest you to have a look at the docs where you can find a bit more description on each of those types, and some of those are just for probabilistic models, as it is the case for the CRPS, and you also have root mean square error, mean absolute error, and a few others that are commonly used in deterministic models. In terms of how do you specify the loss, you can see that in the bottom plot, where basically we use the you will see that a lot in Anemoi training. So we use this target pattern. Basically, what you're doing there is telling Anemoi training which loss function you would use. So in this case, we are choosing one of them, and then you just pass that path to the class in the sort of like target entry. And then there are a few other things that you can specify as part of your loss function, which are scalars. And I will tell you a bit about what are scalars in a couple of slides. This is a bit of a summary of what I just said. So this is a bit of a summarized from the docs in terms of what loss functions we have. So as I was saying, you have mean absolute error, root mean square error, but there is new loss functions, and it's also worth saying that this is a very active field of research. So as new loss functions come up and gets proven useful for the field of data-driven weather forecasting, this is an area of the code base that may change and may evolve in the future. So what are scalars? Well, if you think about let's say graph neural networks and basically how you have a set of breakpoints distributed across the globe, and also the fact that we have sort of like information also coming from different pressure levels distributed across the atmosphere. When you think about how you basically sort of aggregate all that information into a single scalar, and how then you optimize the model, you might realize that you may want a way to nudge your loss function or to weight your loss function so that it basically you can give more importance to certain areas of the globe or certain pressure levels. So the way we do that is through what we call scalars. So there are different types of scalars. In this slide, I'm just mentioning a few. So variable, scaling, pressure level, and node areas. And this is just a way to tell your model, for example, in the plots with the different colors, how do you want to weight your variables? So it might be that for you, precipitation is really important. You might want to give a weight to precipitation that is bigger than what you might want to give to humidity. And then what you see the bottom plot in this slide is basically a pressure level scaling, where you can just also to say, I want my surface variables to be more important than the variables that I have, say, in the top of the atmosphere. So again, you can do that. And the way to do that is through configuring scalars in the loss function section of the configs. Good. So before kind of going through that, I already have given you a bit of an overview of the different configs, but there are a few other things in the framework that I would like to highlight. One of them is what we call schemas. So Anemoi training includes a set of schemas that those are written using Pydantic, and the reason why we have that is to make it easier to validate your configs. So a common scenario that you will find yourself when you want to submit a training is that you have to queue in an HPC, you submit your job, and suddenly you made an error in your config. So you've been waiting for a day, and now you've lost all that time. So to avoid those scenarios, the CLI from Anemoi training includes a sort of command that is Anemoi training config validate, where you can pass your config, and then your config will be cross-checked against the schemas that we have for the different classes in the code base, and will alert you if there is a mistake, or it will tell you if your configs are validated, and then you're good to train. So yeah, this is, again, schemas is also something that gets extended as we include more classes into our code base, but it's something quite useful to then, if you're looking to understand what an object takes as an input, you can also have a look at the schemas, because sometimes they might work as an alternative to documentation. I already mentioned at the beginning that Anemoi training can be used to train models both in multi-node and multi-GPU settings. So I have a few slides to tell you a bit more about these different parallelization strategies that the framework support to allow you to do so. So why do we need to sort of parallelize? Well, if you're trying to train with a big model, so with a model that have a big number of channels, usually you hit a point where your model is not gonna be able to fit in one GPU. So then you might need to think about how you can distribute your model across many GPUs and then effectively train. Similarly, when you have a big amount of data that you want to fit into your model to train, you also can think about ways in which you can distribute that input data across many GPUs, so that basically you parallelize and you make it faster for your model to see data, because you then can copy you can have batches going to the different GPUs. So in this way, you can improve the throughput and make your model run faster. So yeah, there are different types of parallelization strategies within the sort of like deep learning community. And in the case of Anemoi, we support data parallelization and model parallelization or pipeline parallelization. And those is worth saying that those are supported for any type of model. And for the data parallelization, we take advantage of PyTorch Lightning that already provides support for distributed data parallelization. And for the model parallelization, we have custom parallelization strategies to be able to shard our graph across the GPUs and do some smart things also with the edges of the graph, so the computation can scale effectively. So yeah, this is a bit to tell you a bit more nicer in this slide what data parallelization and model parallelization is. And yeah, as I was saying, with the data parallelization, what that means is that different GPUs will be getting different batches. So in our case, those will be different slices, different time slices. And the model parallelization, you basically sort of split your model and you then distribute your model across the different GPU devices. It's worth saying that using parallelization for the sake of using it, if you don't have a need, is it usually not recommended. Model parallelization, the moment you have multiple nodes and multiple GPUs, there is usually an overhead associated with the communication between those devices. And also debugging your code or any errors become more cumbersome. So it's worth keeping in mind that you should strive to optimize your code to use the least amount of resources possible. And yeah, not try to use more resources than what you need. Good. So that's a bit about parallelization. The next thing that I wanted to talk about is experiment tracking. As I said in the beginning, Anemoi training supports common experiment tracking libraries. In this case, the framework supports both MLflow and weight and biases. I'm going to focus on MLflow because that's the one that we use in the community more. So why do we need to track experiments, you might be wondering. Well, if you've done some machine learning or deep learning, you maybe have seen yourself saying, oh, I'm going to change the learning rate now. What about if I now change the batch size? Okay, and now I'm going to try a bigger model. And then suddenly you've run 5 to 10 experiments, and then you have results for all of them, and you want to compare them, and you want to look at that in a month and remember all you did. You need a system to do this effectively and to do this sustainable. So a way to do that is through these type of experiment tracking libraries that allows you to facilitate all this process. And especially when you are developing as a community, it also makes it easier to compare runs that you might be doing. So for example, runs that I might be doing with runs that Harrison might be doing. This MLflow, for example, make that process easier. So the way that the MLflow and weight and biases are supported is through what we call loggers. So in the code base, you should be able to find what we call the Anemoi MLflow logger and the want-to-be logger. Those are the sort of like code objects that are responsible for taking care of MLflow, of the sort of like experiment tracking. And yeah, you can through the target pattern, you can then decide if you instantiate or if you activate MLflow or you instantiate weight and biases when you train. It's also possible to turn this off, but yeah, if you want to enable, you then have to specify which of the two you want to use. And here, this is just an example for those of you that might have not seen one of those before. This is just an example of what the MLflow interface might look like. And in this case, you're seeing how we are comparing the metrics of two different runs for temperature at 100 hectopascals. And then between those two lines, then you can get a feeling for which of the two models is doing better. Yeah, so that's a bit the overview for for the different sections. I think before I hand over to Harrison, I also wanted to briefly talk to you about what do you need to do if you wanted to contribute to Anemoi, because as we said the first day, Anemoi, not just Anemoi training, but any of the packages are open source, and you have this in the documentation, but we wanted to include this also as part of the webinars. The first thing, if you're looking to use Anemoi and you are hitting an issue, is that you should go and try to open an issue in the relevant package under GitHub. So you just go to the package, you click on issues, new issues, you fill the template, and then you submit it. Usually within a few days or within some time, depending on the backlog, you will get an answer from the maintainers or from anyone within the community that will try to help you debug the issue. Similarly, you should do that if you're looking for a feature that you would like the framework to have. And in this case, someone will tell you if this feature is usable or is feasible to be included within the framework, or if this feature might be out of scope for now. Similarly, if you have an issue and you know how to fix it, after opening the issue and discussing this with the maintainers, the next step will be for you to create a pull request. So I would suggest that anyone looking to do that have first a look about the guidelines for opening a pull request, because those are way more detailed in the documentation. But as a summary, you can fork, then you clone the repo, create the branch, and then you open the PR against the Anemoi specific repo. To be able to then get your code merged, you will need to go through a pull request review, get some feedback, if any, implement those changes, and then there will be a final review where that gets maybe approved and finally merged. Then finally, if you are curious to or want to know, for example, about what configs did we use for the different AIFS versions that we've trained here at ECNWF, I would recommend that you check out a repo called Anemoi configs, where then basically you can find the different configs that we used for training or operational version for AIFS version 1 and version 2. It is worth saying that those configs are associated to specific versions of Anemoi, but those are listed as part of the documentation for this repo. So yeah, there you would find these different groups of configs, so the training section, the hardware, and so on, and you will find the hyperparameters that we chose to train those models. And then, yeah, you will have the slides available. So we also included some useful links that includes the documentation for the Anemoi training package, the link to these Anemoi configs, and a few other things for the unit tests and the tests that we run in Anemoi Core that I also suggest as a good introduction for those looking to familiarize with the code. So yeah, that's a bit what we had for Anemoi training today. I'm happy to take any questions.
So that was a very quick rundown of Anemoi training. So wonderfully done by Ada there. So say, it's all worked for you. You have your checkpoint now. We actually want to use it. We actually want to, use the time that you spent on it to prepare the data set, to execute the training, to run it over the large HPCs, and actually get some meaningful results from that. Then we want to run a forecast. Potentially, we want to do it in operations, and potentially we also want to do some research, explore what changes our training configuration, the hyperparameters we perhaps tuned, have made to our model. Anemoi Inference is the place that you do inference. And it is that last link in the chain. That training emits a checkpoint, that atomic artifact ends at a dot checkpoint, and it is fully decoupled. And how we can use it is fully decoupled from how the model was trained. Inference exists entirely independently. It does not have a dependency on Anemoi training. So you're not bringing in those complicated PyTorch Lightning dependencies to be able to run it at inference, to be able to run it in operations. So how Anemoi Inference is built, it's designed to really focus on the inference component. That is why we've split our packages into so many different subcomponents, is to really enable them to specialize. Anemoi Inference supports bringing in different data sources. You can bring in the initial conditions in the data format that you have it. Whereas in training, you run from an Anemoi data set because it's well prepared and it's well done for the speed and the I/O requirements of training. Inference can then go back to the original sources. It can go back to those script files, to those netcdf files that you have on disk, or potentially those things that are coming in real time. We've also got support in there for the model parallelism that Anna talked about, so that you can run on smaller GPUs. You can run it on systems where resources are potentially a little bit tighter. And there are ways as well to chunk it such that it takes longer, but it can use a smaller single GPU as well. And as well, we support integrating it into wider workflows. There's a couple of projects that sit on top of Anemoi Inference that provide an even higher level abstraction. And there's some resources online, some other training courses that will be a part of the Destination Earth MOOC on those sort of topics. So the features and the main headline features that we want to focus on for Anemoi Inference is hopefully how automagical it can be. Because we inject a lot of metadata and a lot of provenance into the checkpoint, we should be able to rebuild everything with a very minimal configuration. So all that information as to which variables you need, which are prognostic, which are diagnostic, which are forcing, are all included in the checkpoint. You don't need to respecify that to run inference. You can just simply use the checkpoint as is. One of the features we're pretty happy with is you can read in one format and you can write out in another format. So you could read in grip files and then output as netcdf. Output is something that you're comfortable and you're used to working with, something that your downstream tools can support. And as well, recent features have supported parallel running across different HPCs, and as well parallelizing the output, because some of these big models, simply writing the output to disk can take longer than the model itself. So that's a really useful feature. So if we just take a quick look back at the models that Anna sort of talked about, and the ones that we can support, you'll get an idea of what we need to support then in inference. So one of the primary models and the tasks that we use is the autoregressive rollout. That is the forecasting model. It takes in t and it predicts t+6. We run that over and over again. Voila, we have a forecast. So that's one type of model that we need to support, one type of task. We also have our temporal interpolation tasks that take in 2 time steps at either ends, they're bookends, and predict some interpolated frames in between that. It is not just a linear interpolation. It is something that tries to encapsulate what is the progression of the atmospheric state between those. And as well, what Anna said, the downscaling. So taking it from a coarse input to a fine input and then making it high resolution with no time stepping involved. That's quite a lot in of itself. That is everything that Anemoi Inference is trying to support. And we are able to do that because we can generalize it into a very simple mental model. We have our inputs, we have our model, we have our outputs. The state flows through those 3 stages. Each of those things that I just talked to you about can be expressed in this way. This is the simple generalization that we're able to use to simplify our pipelines as well. So in our input tensor, we bring in those prognostics, those forcings, and those coupled potential fields there as well. We run it through our model, and out we get our prognostics and our diagnostics. For anything that is autoregressive, we can copy back those prognostics back into the input and run the model again. And we can also do that with our temporal interpolator as well. And as Anna mentioned, I won't go over this in too much detail, each of those variables has a category, and it is training that provides the information as to which category each variable fits into. Whether it's prognostic, whether it's diagnostic or forcing, is captured in that metadata. It is captured inside that checkpoint that we're able to reuse in inference to make it as simple as possible. If we go into how to use inference, there are 3 primary interfaces that you can use. So what we show on our Hugging Face with the AIFS v1 and v2 there is the lowest level NumPy. So it shows you how you can prepare and get an array to go into inference and the array that you get out. With this sort of interface, you have that maximum control. You have every single byte of how the NumPy, how the arrays are constructed. You can modify, you can change, you can bring in your own sources. And it's really useful for embedding in demonstrators like the Hugging Face notebook or in custom code where you need that full control. At a slightly higher level, we have our object-oriented approach. Anemoi Inference exists with classes of inputs, which represent the different data sources. It has classes of runners, which represent the different ways that you can run the model, and different outputs as well. This is really useful for building applications on top of Anemoi Inference. And then for the everyday user, what we run in operations and what you can run for yourself to do research is this command line interface. All of the Anemois, except for some notable exceptions of Anemoi utils and transforms, expose a command line interface that we hope is really simple and easy to use. So for Inference, what that means is that from one YAML config, with one command, we can run our forecast, we can run our interpolation. And it is simple as Anemoi Inference run the config that you've got. And there are two other interesting commands that you might come across. The couple, if you're dealing with any coupled models to exchange information between them, and as well retrieve, which is what we use as well for the generating the retrieval request, because we use Mars and some archives as there as well. And then included here are some checkpoint management tools that allow you to inspect what's inside that checkpoint, patch it, and sanitize it and validate it as well. So I talked about the YAML that did it. I told you it's simple. Here is a true example of what an Anemoi Inference config can look like. And I hope that it's not too daunting. It is quite simple, and it should be quite easily understood by humans being able to read this. It's not a machine format. This is something that you write, that you can read, and you can understand what's happening. So very simply is you tell it where your checkpoint is. You tell it what you want to do with the checkpoint. So for a forecasting model, that's the lead time, how much you want to forecast. You tell it the initial condition depth. And then you tell it where your input is, where your initial conditions are coming from, and then potentially any processing that you need done, whether that be pre-processing or post-processing, and then how you want to save it out. So here I've got an example where I'm getting the input from Mars, and then I'm outputting it to a grid file and also doing some plottings over Europe. These YAML files hopefully collapse quite gracefully and quite nicely. We can simply specify input Mars. It will use all of the defaults. If you wanted to use a grib file, we just have to say input grib and then the file path. And if you needed to go into more detail to control it a bit more, you can expand that further one layer more, and you'll get a more dictionary interface where you can control each keyword argument that is going into those classes that represent those objects. So from there, as I sort of said earlier, all of the metadata which enables this simple configuration, this simple interface, is all stored within that atomic file that is that checkpoint. So turns out PyTorch checkpoints are just a zip file. You can unzip one of the Anemoi checkpoints and you will see the structures. And within there, you'll see an Anemoi metadata.yaml. And inside that, we keep such things as what data sets we use for training, what were the operations that were applied on that data, what's the grid and the area, and how do we map those variables to positions in that input tensor to ensure that where the model expects to see 2-meter temperature, it is indeed getting 2-meter temperature. It's not getting Z500, for example. And this is all done to allow Inference to set up its pipeline automatically and have really those simple configurations. For some details as to what we have available in the inputs, here are a cutout, a selection of the inputs that we have available. You can grab from different sources such as Mars, CDS, and it really enables that ability to grab your initial conditions from whatever format, whatever place they're in already. And within this, we also support NetCDF and some simple dummy tests if you just want to check if your model can run. And then to enable those nested stretch grid models that Murray would have talked to you about, and what we talked about a bit on the first day with Anemoi datasets, the cutout input does that same operations to nest those local areas with those global datasets there as well. Data is weird. I hopefully don't have to tell too many of you that. It comes in many different shapes and sizes. The processes that we have available in Anemoi Inference help transform that state into something ready for the model. And within this, we can point back to Anemoi transforms to the exact same processes that we use to prepare the data set. So we can mirror that pipeline and mirror that approach to really enable the data that's going into the model to be consistent between training and inference there as well. For outputs, there is a selection of them as well, and it's just as pluggable as the input and the processes are. So we can just simply print out the min, mean, max of a field. We can write it to grid NetCDF ZAR. We could even plot it with EarthKit plots. And then each of these come with different configurations to subset the variables, to control the output frequency, to do some further post-processing. And a recent feature that we actually merged today, the parallel output, which for models that are starting to become quite high resolution, say as we move towards a 9-kilometer model, that output cost of writing to a file does take quite a lot of time. So with parallel output, we can split up that workload and have multiple workers each write a subset of the data to remove that write bottleneck that we might encounter in operations. And as well, if we just go a bit more into the parallelization aspect, we also have the runner parallel, which allows us to distribute the model across multiple GPUs. And it has support for auto-detecting the cluster, the HPC system, that you might be running on, whether that be Slurm, MPI, or you've set it up via Torch Run. And you can control as well the memory with the Anemoi Inference num chunks environment variable there as well. So I showed you the slide on the Anemoi datasets lecture. We talked about what does Anemoi enable. I told you Anemoi datasets enables those different applications. Maybe I'm biased, maybe it's because I work on inference, but I think it's Anemoi Inference that enables these. It's what produces this data that goes in to make these pretty pictures. And it just really shows that the ecosystem working together of Anemoi is what enables these different applications. We have that consistent pipeline between datasets through to training, through to inference, and it simplifies and it makes it easy for scientists, for researchers to build these different models, to explore machine learning for weather forecasting. And it is something that we are quite proud of and excited to see what people can do with. Thank you very much. Hopefully, we have sorted out some of our technical difficulties. Hopefully, we have enabled the Q&A. There is a Q&A thing probably in your top area there for questions. And I think the chat might be working. So please post your questions there.
Yes, we have so far a few questions in the chat, Harrison, that I've not yet answered. And then on the Q&A side, I don't see anything yet. Not sure, Julia, if you want to start going through the questions in the chat or yeah.
Yes, thank you. Let's have a look at the chat. There's one from Jun Wang for the multiple time step output. So for example, with T6, T inputs and output T plus 6 and T plus 12, and at the next rollout at T plus 6, we also get output at T plus 12. Which T plus 12 from time T and from T plus 6 is the final output? Okay, sorry, maybe you want to have a look at that in the chat yourself.
Yeah, I mean, basically what I would just say is that I can try to reply that later, but for multi-step output, you have to, the benefit of this technique is that actually you reduce the number of rollout steps. So you don't have overlapping times, but rather what you do is that you reduce then the number of rollout steps. So you don't have to do every on the frequency, but rather taking into account the buffer that the multi-step output introduces. I hope that answered, but yeah, I will try to also reply to that written down so it's a bit clear.
Thank you so much. How can we access AIFS ENS, so AIFS Ensemble, historical forecasts? Does Anemoi provide such data as well?
So for that one, AIFS ENS is archived to the Mars system at ECMWF. So it kind of links into the question above it. So yeah, you'll need a license to be able to access that Mars data. Anemoi is simply the tool to run the AIFS ENS, would not necessarily provide that data as well. And if I was going to answer the question above it, yes, you need a license to access Mars data of the AIFS. You do not necessarily need a Mars access data for Anemoi. You could use the data that you have available yourself. If you're interested in initializing the AIFS models that we have made available, there is a 3-day rolling initial conditioning and forecasts available for AIFS and IFS on our open data service. So that is data.ecmwf.int. And the analysis state for IFS is sufficient to initialize the AIFSs, and that is what we show on our Hugging Face notebooks there as well.
Thank you. We'll put the links into the chat as well. Is the parallelization applied to the compressed output data?
I'll take that one as well.
Yeah.
So the parallelization of the output paralyzes the output classes themselves. So it is applied across the tensor that exists on the GPU, and then each of those take a subset and then write it out. So it's applied before any compressed output data. Each output can then provide its own way of writing the files.
Thank you. Since the forecast lead time increases up to 240 hours ahead, how does forecast reliability evolve with lead time? What metrics would you recommend for verification?
I can take that one, but Harrison, feel free to also chime in, as I think I'd be also interested to hear your thoughts. Essentially, I assuming that with reliability you mean how much we can trust the forecast. What you usually see is that even with physical models, then the uncertainty grows as we go to higher lead times. So then basically the model doesn't rely so much in the sort of initial conditions, and the errors start to accumulate as you roll your model during more steps. So then these two factors means that your forecast will become more uncertain, and usually the error is bigger. The way we usually measure this is that we basically compute the forecasts for 10 days, and then we measure these with things like the root mean square error, but then other things like activity and different metrics that allow us to see this. Harrison, you have anything to add there?
Not particularly. I think we're up to actually 15 days at this point. It's a standard verification metric, so comparing against observations and the like there as well.
Thank you. So far, Anemoi has mainly been demonstrated for rollout forecasting. What other applications does the current version support, particularly in areas such as spatial downscaling, super resolution, generative modeling, and learning multi-scale atmospheric representations?
Well, without disagreeing, I think that Anemoi has also been demonstrated for other areas like temporal downscaling. And there will be this is still under active research. I think there will be some publications coming soon to show some of these models. And then for generative modeling, as I said at the beginning, actually you can also train probabilistic models using diffusion. And when you say learning multi-scale atmospheric representations, well, I would also challenge to say that for the regional modeling with approaches like the stretch grid or even the LAM, you are combining grids from different resolutions. So the model is actually being able to learn the patterns from the different regions, and those being different resolutions. And I think spatial downscaling there is actually some work that has been done within Destination Earth that also shows advancements here, and those are based in Anemoi. It's just that at the moment we are working on integrating them into the sort of like main repositories.
Okay, thank you, Anna. Very clear. Next one. Could we use AIFS to run subseasonal forecasts and get results comparable to IFS, or run ensembles with more members than the original forecasts?
Harrison, you want to go?
I can take that one. Yes, you could theoretically use the AIFS, and you can run them out to any lead time that you so wish. The next part of the question is get results comparable to the IFS. No. We do see degradations at those longer lead times for the AIFS single. AIFS-N, due to its nature being trained for a probabilistic score, is slightly more stable, and it does remain more skillful at longer lead times. There is work ongoing to explore an AIFS variant that is optimized for the subseasonal forecast ranges. So keep an eye on our publications and our repositories in Hugging Face if you're interested in that. Regarding running ensembles with more members, AIFS-N itself, yes, is non-deterministic itself. So what that means is that you could run it on the same initial conditions over and over again, and you will get a different forecast. By that, you can get a weakly dispersed ensemble, and you can also then explore putting it on perturbed initial conditions to then enhance that ensemble. So yes, you can generate a super ensemble if you just keep running it over and over and over and over. Okay.
Great. Thank you. To improve training for better small-scale radar reflectivity, especially its movement, what should be considered? More levels in the lower troposphere or larger scaling for CAPE or REFC?
Sorry, I was just adding the information about the weather quest to add to the question from Harrison. Let me levels. I'm not too familiar with CAPE or RFC. I don't know, Harrison, if you want to comment on that. I would just say that in general, if you are trying to kind of like look at variables that are closer to the surface, what we've seen there is that then the spatial resolution and the temporal resolution do matter more. So basically, when we were going, for example, from our first to our first operational version, we did see that the resolution mattered more on the surface variables. And then, yeah, I would say it's a matter also of having, I guess, if you have observations, making sure that those are that the quality of the observations are good and they are not too noisy, because that's also something that might affect your model. I don't know, Harrison, if you want to add to that. I guess also the only thing is, the other thing that you've not mentioned there is you would also need to think about the right loss function to then basically try to see if you want your model to capture any particular spatial scales more sharper. It might be that the root mean square error then might not fit the purpose.
Yeah, only thing I'll add to that, in a lot of things, this is an area of ongoing research. So applying the Anemoi packages and stuff to that nowcasting regime, to the radar regimes. There is a paper published 2 days ago from colleagues out of Met Norway that did explore different elevation studies with radars. So if you're interested, take a look. It's hot off the press.
Thank you. We have one from Zainab. Is the loss computed equally across all forecast lead times, or are certain lead times weighted differently? Are +6 hours and +24 hours the same? Is there any extra importance for longer term?
At the moment, we don't induce and we don't include any sort of scalars along the time dimension that will let us like nudge the model more for the sort of like early lead times. It is usually the sort of like training regime that we have been using for training something like AIFS include first a period of what we call pre-training, where basically the model is trained for just one step ahead. And we train the model for 0, 6, 12 and 18. So the model see all the sort of like initializations at the same frequency. And then we have a sort of second stage of the training that we refer as rollout. And here we run, what we do is that we run the model from rollout 1 to sort of 12, so up to 3 days ahead. And we aggregate the metrics around on the rollout window. And here we don't sort of introduce any scalings, but you could argue that because the rollout runs progressively for 1 to 12, the model do see more cases at the sort of like early lead times.
Great, thank you. I don't see any more questions in the chat, and we're past the hour, so I would say thank you very much. We will be uploading the webinar recordings, the presentations for you at a later time. I put the link in the chat, but in any case, it's the same event webpage. Thank you so much, Anna. Thank you so much, Harrison. If there's any more questions, feel free. You have their emails. You have our email, training@esnwf.int as well. Reach out at any time, and we hope to be seeing you soon. Bye.
Thank you so much. Bye-bye.